Hi, and thanks for joining me. Today I'm going to talk about heterogeneity and social structure and why they matter for pandemic control. I'm also going to talk about cultural evolution and how I think it can help us make some sense out of heterogeneity and social structure and transmission dynamics. So start by acknowledging it's been a pretty tough road the last year. We're already in 2021, and we've still got a ways to go for complete pandemic control. And so I think that the lessons that we're learning right now can still be applicable to our current COVID situation. And of course, we hope to prepare better for the future for inevitable pandemics that are going to come down the road. So with that, let's just start talking about social behavior and transmission dynamics. Every transmission event in an infectious disease has a social cause. For transmission to occur, a susceptible individual has to come into contact somehow with an infectious individual in a manner that allows successful transmission to occur. The contact doesn't need to be direct or even simultaneous, right? You can have something like a waterborne or a fomite mediated infection, but people have to be in the places that allow the transmission to happen. And that is dictated by social behavior. For a directly transmitted disease such as COVID, what brings people together to the same space, right? Where the pathogen can be transmitted through aerosol or through droplet. So these are fundamentally social questions. And in fact, right, the social behavior is embedded in the formalism of transmission dynamics models. We have an SIR model here, well-mixed model, unstructured. So I dot is the time derivative of the fraction of the population who's infectious. And what we've got is the social behavior is embedded here in this mass action term where, S is the fraction susceptible, I is the fraction who's infectious, and beta is what we call the effective contact rate, right? It's the mean contact rate of individuals within the population times the transmission probability conditional on contact, right? And so that's a well-mixed population. Everybody can kind of interact with everybody else in bilinear proportion to the fraction, right, susceptible and infectious. We can add structure to the model, right? We can say that there are some number of compartments, and here the social behavior is broken down by these different categories. The number of infectious individuals in group I is the number of susceptible in group I times this the sum of these different products of the contact rate, the effective contact rate, and the fraction infectious in the different categories. Right, and we can continue to substructure the population according to categories, and eventually in the limit we get something that's like an explicit network structure. But know that we still need to have a generative theory of why individuals have the contacts that they do. What makes the structure? Where do the contacts come from, and what motivates people to make them? We also need to think hard about what the network actually is, right? In a case like this, where we have an explicit network structure, is a tie between two individuals there because there's a potential for transmission because maybe they're in the same social space or something like that. These are social science type questions. And I just want to take a second and note that there's really interesting deep connections between the way we measure social structure for the types of structured models that I mentioned here and the network models here, and work has been done by Martina Morris and Steve Gaudreau and Lord Achille on this, relating the way the way that network models are deeply related to these cross-classified models of social structure. Martina has been a leading proponent for integrating social behavior into dynamic models, and has probably done more than anyone alive now to further that. And I think that there are actually a lot of open questions still in this area. The network epidemiology is obviously very, very hot as well. And I think it would be great if more people, more social scientists got engaged with working with infectious disease modelers, and more infectious disease modelers got interested in these social types of questions. All right, so that's what the rest of my talk is basically going to be on. But let me start by talking about where I was sort of the end of 2019. I've always worn two hats. I'm an evolutionary anthropologist. I'm interested in questions of life history theory and livelihoods and that sort of thing. And I've been engaged in what you can broadly call evolutionary economics. We wrote a paper that had a camel in it, and camels get clicks. Apparently, that's what I've learned from the media people at Stanford. Camels get clicks. And my former PhD student Mike Price and I have written a couple papers that are published or in press. And the kind of big takeaway argument of our work in evolutionary economics is that while formal rationality has taken a big hit in the public imagination and in lots of sort of popular work, the often peculiar behavior that's observed by behavioral economists and experimental psychologists actually makes good evolutionary sense. Humans seem to be, in a word, evolutionarily rational. Okay, so that's two words. But that's our broad argument. And I'm actually working on a book that makes this very argument. Okay. So that's my first hat, evolutionary anthropologist working on life history and decision making. My second hat, is working on disease ecology and the social behavior underlying diseases. And, working in at the end of 2019 with colleagues at UCSF, Travis Porco and Dan Kelly, and others from the Proctor Foundation, and Gene Richardson at Harvard, who's my former PhD student, and a bunch of people there trying to figure out, can we develop novel contact tracing and vaccination strategies for stopping the rapid spread of Ebola, such as during the outbreak of 2014 and 2015 in West Africa, right? And can we come up with essentially clever algorithms to optimize our contact tracing and our vaccination? Well, January 2020 comes along, and Andrew Neumer always has a colorful way of talking about things. And I think that this has really come to this premonition has come to bear. And so you start to see the images rolling in of the US pandemic experience, particularly in the United States. They come pouring in, and it proved to be a really tough time, it turns out, on the one hand, to be writing a book on human rationality. It's also a tough time to be formulating clever algorithms for optimal vaccination strategies when it turns out that large swaths of society don't even believe that the epidemic is real or that it's serious. And sometimes they actually actively work to undermine control efforts. Tough time to be doing the two things I was doing. So this has caused a little bit of a shift in my thinking to focus on problems like individual versus group rationality and how to affect behavior change when socially maladaptive behavior gets incorporated into people's identity and they form social groups around that, right? So, just to reiterate, how can I possibly make an argument for a general rationality of human decision making in light of what we've seen in response to this epidemic? And more importantly, how can people who make such good decisions, as I suggest in this book and in the work with Mike Price, when left to their own devices, particularly when they're highly constrained in their decision making, how can they make such bad decisions in groups? And just as a quick pointer to people having good instincts about these sort of things. Here's the great Randall Munroe from XKCD, wrote this comic in May of 2020. And he notes that 86% of Americans say stay-at-home orders are responsible government policies that are saving lives rather than an overreaction. And we have all these similar results from multiple polls. And I just want to point out, for context, 70 or 25% of Americans believe that the Earth does not rotate around the sun. So to have 86 to 93% of Americans agreeing on science-based public health interventions for the broader social good is a remarkable figure, okay? But when people get together, they seem to lose some of this sensibility. So how do we go from what seems like very reassuring results from surveys of individuals to the collective craziness we've observed during the pandemic? Working against public health interventions, of course, greatly prolongs the pandemic, right? It makes things worse. It affects more people, it kills more people, it draws out further the need for further control. And I kind of think of this as the Band-Aid theory of control. Either you rip it off, in a quick but sort of harsh intervention, or you draw it out for an excruciatingly long period of time, right? And we seem collectively, we seem to have chosen to beat ourselves up and do the latter. Um, we've got all manner of people actively working against infection control, and of course, thereby making things worse. And it's not just sort of what we'd like to classify as sort of crazy people on the far right, right? They're people who otherwise are probably pretty sensible, uh, middle class, not extremist folks who are really upset and about public health interventions. It seems that mask wearing is a particular sort of flashpoint. There's clearly a real semiotics to covering your face and masking that bothers people, right? Um, and so I think that this has caught a lot of people off guard, right? And how do we explain this? How do we handle it? How do we make it better? I think that cultural evolution can help. And I'll just talk about this for a couple minutes. And most of the rest of the examples that I talk about deal in one way or another with cultural evolution. So, in 2015, Joe Henrich very forcefully argued that the secret to human success lies in culture, and in particular, it's cultural learning. Cultural learning, particularly processes such as conformist bias, can greatly accelerate the adoption of adaptive traits, as indicated by the black line here versus the red line of individual acquisition. Right, individual acquisition would come about through trial and error learning. It's a much slower process. It's much faster to copy what appears to be successful behavior of other individuals, and it can lead to a very rapid adoption of adaptive behavior. There's a fundamental trade-off, though, and this is something that I don't see discussed a lot in the cultural evolutionary literature. Here's a simple formula for default. So you default, or you become destitute when there are two failures, okay? And this is a joint failure of two Bernoulli random variables. And the default correlation calculation is largely driven by the correlation between the defaults of events I and j, right? So if we just assume that the p's are let's call them equal, and that they're small, right? There's a low probability of failure of each of our different outcomes. Then this can reduce down to basically this right, that the probability of destitution is p times rho, and rho is not small, right? And in order for this very rapid cultural evolution to take place through conformist learning, rho is actually typically very high, right? We induce correlations through social learning, and so we open ourselves up to vulnerability. And I think that explains a lot of what we're seeing in epidemic behavior. And it turns out that some smart people have said this before. It's just not a super highly cited paper. It's an interesting, great paper. Hal Whitehead and Pete Richardson said this in 2009. And they pointed out that when you learn primarily through conformity, you actually, once that conformist bias and the learning goes to fixation of an adaptive trait, you can decouple, right, people's behavior and their adoption of behavior from whatever environmental signal they're originally responding to. And this can lead to catastrophic outcomes, as we see in their figure here. So there is a history of doing this. This is a very active area of research for me right now. And I think it's important in the context of the pandemic because uncertainty activates social heuristics. When we are faced with an uncertain situation, we fall back on these social heuristics such as conformist bias or prestige bias, okay? And I think it's easy to forget, because it feels like we've been dealing with the pandemic forever, right? But this is really a brand new infection. This is a zoonotic spillover that happened just over a year ago. And, at the outset, we didn't know how severe it was. We saw lots of terrifying images from China, these cities with, of 10, 20 million people with empty streets and horrifying pictures of hospitals and that sort of thing. And then as it came to the rest of the world, we saw horrifying pictures from New York City and from Bergamo and in Italy and from all over. But, I think that in some ways, the fact that the SARS coronavirus 2 leads to mild to moderate illness in most people just increases the uncertainty, even as we learn more about it. because it provides just enough plausibility for deniers' arguments. And deniers there have been. There are plenty of deniers, right? We've seen it at the top of the US federal government. Politicians, many politicians are motivated to downplay the risk for political purposes, right? And this injects a great deal of uncertainty into what's already an uncertain situation because of the novel disease. We also have what appear to be experts, right? Nobel laureates in physiology and medicine coming out and saying, absolutely, this thing will be over by August 22nd. That was 4 weeks from when this tweet was sent out by Nobel laureate here, a Stanford professor, very smart guy, not an epidemiologist, okay? But he certainly has a great deal of scientific cachet and influence, right? And so, how did it go for this prediction? Well, there's August 22nd. And our narrator can chime in at this point and says it was not over by August 22nd. Okay, so we have the point here is we have an environment that's suffused with uncertainty because of the inherent uncertainty of a novel pathogen, because of the active muddying of the scientific and policy waters by politicians and by people who seem to be experts in science more broadly. All right, so what do you do in an uncertain environment? Well, there are a couple different uh, takes on this from evolutionary cultural theory. And so Pete Richardson and Rob Boyd wrote the classic monograph on cultural evolution, 1985, and they talk about specifically this case, right? When faced with uncertainty, you fall back on heuristics such as conformist bias. Joe Henrich, who was Rob's student at UCLA, right? They wrote a paper in 1998, sort of further elaborating on this. And this seems to be, there's a lot of intuition behind it, right? If you don't know how to respond, look at how others are responding, particularly if they're doing okay, right? And so you can actually combine different heuristics of conformist and possibly prestige bias, okay? Another idea comes from this terrific review from 2006 of Marty Hazelton and Daniel Nettle, which they titled The Paranoid Optimist, an integrative theory of an integrative evolutionary model of cognitive biases, right? And they have this idea of what's called error management theory. And the basic idea is that making mistakes is inevitable, but some mistakes, false positives versus false negatives, right, are more costly than others. And depending on the type of decision making that you're going to be doing, sometimes a false positive is more costly, sometimes a false negative is more costly. And the suggestion is that over evolutionary time, as we face these types of problems, we are going to bias ourselves to make the types of errors that are least costly on the balance. And one of those types of errors seems very likely to be imitating others who are successful around you, or at least who aren't dead around you, right? That success has lots of different levels. So this is a really interesting evolutionary foundation for a ubiquitous process we see in the social sciences, which is that it turns out, right, that people don't associate randomly. I've got two groups of two types of people here. I've got the waivers, we can call them, and then, we've got the silhouette of the woman kind of standing in a jaunty way. Let's call her a hipster. We've got hipsters and waivers, right? And here we've got a more or less random association. But in fact, what we typically see uh, aligning along nearly any social category, right? Age, income, race, education, sex, whatever. We see what we call homophilous association. So like associating with like. And as we'll see, this has enormous implications for the transmission dynamics and the control of infectious diseases. All right, there's been a lot of work on homophily in general, and particularly with contagious processes. I'll show you four quick pieces of work on this. Sinan Aral in a natural experiment showed that 50% of behavioral adoption could be attributed to homophily, right, in this natural experiment he observed. Damon Santola did behavior change experiments. They weren't natural experiments. He actually did the interventions, and what he found is that adoption of health behaviors increased tremendously in the presence of homophily. Nicole Crienza and Mark Feldman from Stanford, right, showed that trait selective advantage need not be as high to spread when it's transmitted assortatively by bearers. In other words, when there's homophilous social interaction. The criterion for success can be lower if you tend to imitate people around you anyways. Um, and finally, another Stanford team, Ben Golub and Matt Jackson, showed on strategic interaction networks, right, that homophily will slow convergence to best response in strategic networks. So that suggests, right, that people are doing the sort of things that their alters in their sort of social neighborhoods are doing. And these last two papers begin to hint at how homophily can be problematic, right, for transmission processes. All right. So I'm very lucky to be the PI on an NSF grant related to COVID with this fantastic team of young scientists. And we are studying a lot of these types of processes. I'm going to talk about a paper that Paul Smaldino and I have written already on this topic. And it deals with the question of when public health compliance becomes an identity, both an individual and a group identity. And what we do is we construct what we call a coupled contagion model. We have two different types of contagion happening. On the one hand, there's the infectious disease transmission, right, which is we follow a standard SIR formulation for the infectious disease. On the other hand, we have a cultural contagion, right? So a learning process, and this follows an SIS model, a susceptible, infectious, susceptible. You can go back and forth between being receptive to adopting the idea and losing the idea and picking it back up again. Okay, and so here's a state diagram that basically shows the sort of standard state model. Susceptible become infectious, become recovered or removed at certain rates, right? But we've structured the population into two groups that we call careful. Right? These are people who have adopted an adaptive cultural behavior like wearing a mask or engaging in social distancing, and we have uncareful people. Right? These are people who are not protected. They have this sort of baseline probability of infection. We build in homophily. Now, and I should point out that all of the papers that I reviewed previously, they all dealt with what's called uniform homophily. We incorporate a phenomenon called differential homophily, so that two groups might be more or less homophilous than each other, right? So group one with homophily, the rate of interaction within group one of W1, right? W1 could be different than W2 for group two, right? So some groups are more cohesive, some groups are less cohesive. And it turns out that differential homophily actually has a big role to play in the in asymmetries in the spread of things more generally. All right, so we have this learning model. We couple our learning model to our transmission dynamics model. And I've talked about homophily, but there's actually one more element that's essential to Paul's and my model, which is we got to add to the mix outgroup aversion. Here's an amazing picture from Huntington Beach, which is kind of the West Coast capital for this kind of stuff. These in-face clashes where different groups come together and they don't like each other very much, and they are actively doing the things that the other group doesn't do. So there's an outgroup aversion in our learning model as well. If I'm in group one and I look over and see what group two is doing, whatever they're doing, I'm going to do something different, okay, with a certain probability. And we can tune that parameter and see what happens with that. We got different types of behavior emerging from this, whether or not you engage in protective behavior, properly calibrated protective behavior, or whether you do not. Okay, and so let's look at the effect of homophily and outgroup aversion first on behavioral adoption. Depending on the strength of the homophily, depending on the strength of the outgroup aversion, we can get very divergent types of adoption dynamics. You can get, at the most basic level, you can get two groups that end up in the same equilibrium, but one gets there faster. all the way to D here, where you get just a fundamental bifurcation. If the outgroup avoidance or the outgroup aversion is strong enough, we can get this bifurcation where group 1, basically everybody adopts, and group 2, essentially nobody adopts. This is an interesting condition because it is suggestive of elements of the social landscape of the United States under COVID. So we couple our model to a transmission dynamics, infectious disease transmission dynamics, SIR model. And again, we get a wide variety of possible dynamics. I'm going to draw our attention to this subplot H here, because this one's really interesting. What happens? Well, at the outset of the epidemic, it starts in group 1, and you get a little increase in incidence, right? But because of the protective behavior that is actually protective, this goes, the adoption of the protective behavior goes very quickly, and it goes nearly to fixation. And what that does is it reduces the force of infection in group 1. And the outbreak initially is quite small, okay? But this is where the outgroup aversion comes in. So now group 1 is essentially at more or less fixation for this protective behavior. Group 2 is going to be much slower to adopt it because of their outgroup aversion towards group 1. And what ends up happening is that the force of infection is much higher in group 2, and you have a much worse epidemic. Right? Eventually, it runs its course. It has a classic incidence curve shape, an epidemic curve shape. And then there's a little bit of a rebound here, because remember, it goes both ways, right? And maybe that's not super realistic about this model, but you get a little bit of an echo in group 1 as a result of the group 2 having adopted in larger measure the protective measures. All right, so we wrote this paper in April and May. It's been through a long process of review. We're hoping it's very nearly over the last hurdle. It may have seemed prescient in April. It now kind of seems descriptive, right? This looks a lot like what we've seen in the U.S. in terms of the timing and the severity of different epidemics. All right. So that's an evolutionarily inspired model. What are some more ways that cultural evolution can help? And I'll just take a moment and say, so many of the problems that we face in the world, pandemic control being the most immediate, but climate change and fighting runaway economic inequality and fighting racism, all of these things involve behavior and culture change. And we actually have a science of culture change. And it's small, and it's largely unknown outside its core of practitioners. And I think we need to change that. And I'm going to show you a paper that I was not involved with, but I think is really terrific, by Charles Everson and colleagues, Sonia Vogt and Ernst Fair. And they make the really keen observation, right, that in a population of cultural adopters, you typically have heterogeneity. You have people who are more or less responsive to change. And when you have a population that's composed of a mixture of these two kinds of people who are responsive and people who are not responsive, what it sets up is the possibility for bistability of your equilibrium, so that you can have a largely adopting equilibrium, you can have a largely non-adopting equilibrium, and you can have an intermediate unstable equilibrium. And where you end up depends on where you start and what the sort of the magnitude of the shocks in the system are. Okay, and this is really, their model is really about the responsiveness to conformist bias, right? Because it's about trying to seed behavior change and then get the rest of the in a relatively small seed, and get the rest of the population to sort of fall in line with that through conformity and imitation. So their paper, the very smart cultural evolutionary scholar at the London School of Economics, Michael Muthukrishna, wrote a companion piece to this. And he writes, right, that the first lesson from the models the Everson et al. Models, is that targeting those who are most amenable to change is easiest for policymakers, right? We like to target the low-hanging fruit because we like to show early success of our interventions. And so it's very easy to go for the people whose behavior you can change most easily. Going back to the Muthukrishna quote, but it's least effective for triggering successful spillover. So in other words, cascades of behavior change as a result of social processes. Campaigns targeting amenable families rely on the most resistant families endogenously changing their preference and behavior, which is less likely, right? So by seeding the population, right, with the low-hanging fruit, you're left with a nearly impossible task of switching over the most resistant people. So the clear implication of this, right, is that ideally, you actually want to try to initially target the most resistant people. This is going to be hard because you want to show success of your intervention. But if you're going to have any hope of getting these sort of cascading social benefits of adoption, you need to work on the most resistant people first. And this is a fundamental, and it's a cool insight from this evolutionary framework. And it's got me excited about how we can think about applying this in pandemic control. So here's just my redrawing essentially of their figure as I've tried to reverse engineer what they did. You've got two groups. You've got the standard, sigmoid adoption curve, which is really standard in the innovations of literature, right? You start off slow as you pick up, you get near exponential growth. You get an inflection point, you slow down, you got this concave approach to the final equilibrium, and at the final equilibrium, everybody has adopted. But you've got this second subgroup, right, that is more likely to engage in the behavior when no one else does, right, and is less likely when everybody else does. And you can compose a total population as a mixture of those two things, and that's what gives rise to this bistability, where you have the stable equilibria, there's a high adopting equilibrium, there's a low adopting equilibrium, there's an unstable intermediate, and you get pushed to one of those two stable outcomes depending on initial conditions and the nature of the shocks in here. Okay, so that's their model. What if we take Paul Smaldino's and my model, where you have actual antagonism? If group one has adopted at a high degree, group two is less likely to. So we change the sign on our sigmoid curve, and we get an attractor that looks like this. We have bistability again. There's a much larger space where you get essentially intermediate adoption, and that's stable. But then you get this really interesting and kind of convex looking curve moving away with the bistability again. And what I take away from this is really important. Is that, note, this is the proportion of people wearing masks, even when the population structure is really propitious for adoption of mask wearing. There is this stable lower leg of our attractor here, right? We still have these bistable conditions, and you can imagine getting pushed down to that. So we need to think very carefully about heterogeneity, right? If this is what the population looks like, but we're just treating it like it's the black line of adopters, we could very easily end up in the bad equilibrium. And these are the types of questions that the evolutionary approach asks. We can translate this into a more sort of network centric approach. And so suppose we have, structure in our population. The people in Sion, if we initially just at random sort of start intervening in the magenta population, right? The people back here in the Sion population are going to have zero exposure to that. There's no way that you're going to be able to spill over an intervention by seeding it down here in the entire, sort of a meta population. What we need to do is identify these bridges between the communities, and those would, my hypothesis is, they would be the ideal individuals to target in a population like this. They have the highest betweenness centrality, and interestingly, this ties it into some of Damon Santola's work, right? That individuals who have high betweenness centrality here tend to be a little bit peripheral to their local cores. And as Damon has argued in his latest book, and perhaps paradoxically, innovations are more likely to diffuse from the periphery to the core than vice versa. And so if we want to send a behavior change message into this whole network, we should be targeting these individuals in blue with the high betweenness centrality so that they can actually help it diffuse out in either direction. All right. So heterogeneity and structure matter a lot for behavior change. We've got supporters of the Patriot Prayer and People's Rights Washington marches here, showing their unhappiness with pandemic control measures and changing behavior via spillover, via these cascading social events, stops working when harmful behavior is really central to the group's identity. And the question is anti-control measure really central to the Patriot Prayer League's identity? I think that there might be some hope for this one, because it's not like wearing a mask is or engaging in social distancing is deeply embedded in any group's identity, any pre-existing group's identity. What's happened is it's rapidly been brought into other existing concepts, right? About control and freedom and individual autonomy and your responses to the state and that sort of thing. I think that this opens up possibilities for breaking these complexes of sort of co-evolving cultural traits. And one obvious way to think about this is to switch over to prestige bias. This is Stone Cold Steve Austin. He was a quite famous professional wrestler and quite a character, very charismatic personality. And Stone Cold Steve Austin has actually, I think done some good in the COVID pandemic. Here he is with, posting on Instagram to his at least 1 million followers. I forget how many exactly he has, but it's well over 1 million. And, he's modeling good protective behavior. He's got a mask on. It's a cool mask. His friend made it for him with his school logo, right? And you'll see that there, at the time that I screenshotted this, there were well over 3,000 comments on it. And a lot of them were of this type, the mask goes against your reputation. Stay strong, be a rebel, and do not conform. Cool mask, but strip off the communism. And Stone Cold Steve Austin is just like, shut up, dude, right? Like, be reasonable. So if we get some more Stone Cold Steve Austins, right, people who appeal to the types of demographics that have been engaged in this sort of anti-pandemic control behavior, I think we have a hope of possibly breaking up some of these co-evolved cultural complexes. All right, so the one last point I really want to make is that heterogeneity, it's not necessarily evolutionary, but it does depend in a profound way on selection. And it has to do with what the critical vaccination threshold is. And in the discussions of the Great Barrington Declaration, and whether we should just let the pandemic run its course and provide herd immunity, there's been a lot of wishful thinking, I think, about making real observations, right? Real observations that it does seem like the force of infection slows down after about 20% of the population has been infected. And this has led a number of people, including some very smart people, to suggest that the herd immunity threshold, which we predict to be on the order of 60 to 70% of the population, because in a well-mixed population, it's 1 minus 1 over R naught. And if we take, this is a reasonable range of R naught here, and say 2.5 as a sort of reasonable intermediate value, then that means that the final size will be 90% of the population if nothing happens to the epidemic, and the herd immunity threshold will be 1 minus 1 over that, so 75% of the population. Okay, and so one suggestion has been, well, maybe there's enough heterogeneity that in the population that really the herd immunity threshold is actually closer to 20-25% and not 75-80%. And the logic of this goes something like this. Here's a network I constructed using a negative binomial degree distribution. The degree is the number of edges that are incident to a vertex, right? And the distribution is essentially the number, the contact rates, the frequency histogram of the contact rates in the population. And it's a skewed distribution, right? It's a negative binomial with a substantial right skew. So there's some individuals who have a lot of contacts. Most individuals have fewer, right? We can highlight a particularly well-connected person here. What do we do if we take out, what happens if we take out the top 5 highest degree individuals in this network? What we're left with is a prune network that looks like this, and it's much less amenable to a big outbreak. We get breaking off of multiple components that are disconnected. We get big holes in here. We get generally less connectedness, fewer opportunities for a large epidemic. And that's only taking out 5 individuals and their contacts. This is a phenomenon known as network frailty that Matt Ferrari and colleagues talked about. And it's clearly something that happens, right? Because the people who are the most at risk, right, are the people who have the most connections. They're likely to be systematically removed from the population faster. So it's like a frailty process. The most exposed, the most at risk are the first to exit the population. And you get these prune networks like this. So is this a reasonable thing to expect for a respiratory transmission, a respiratory virus? Marcel Slatte and I in 2010, with a bunch of colleagues, measured for the social context in the context of the last pandemic, a much smaller pandemic, the H1N1 influenza pandemic. We measured contacts in a school using these wireless sensor network motes that students wore around their neck, and they measured face-to-face contacts of 2 meters or less. And what we can do is construct essentially a degree distribution. It's strength, so it's a weighted degree distribution. And what we see is that these are not very skewed distributions at all. A normal, just a single Gaussian fits quite well. A 2-component Gaussian fits a little better, but it's really more about the excess in the shoulder than it is about the tail. And so the reality is, in a respiratory pathogen, there isn't that much heterogeneity to prune out through frailty. Instead, I think what we're seeing are sort of natural processes that relate to the underlying behavior. This is Ronan Arthur, who led a paper that just got published last week in PLOS Computational Biology. Ronan was my former PhD student, and he was joined by a group of super smart collaborators. And we show that adaptive behavioral responses to epidemic conditions can easily lead to cycling and other more exotic behavior. Given such cycles, it's natural to see declines in incidence in transmission processes, in any transmission process that has a lot of social input to it. So we write, under small perturbations, the model exhibits complex dynamic regimes, including oscillatory behavior, runaway exponential growth, and eradication. These are all possibilities depending on the specific conditions. The dynamics suggest that for epidemic responses that rely on social contact reduction, as we do in COVID, secondary waves and surges with accompanied business and school reclosures and shutdowns may be expected, and that accurate projection under such circumstances is unlikely. So I think that what we're seeing is not the fact that there's a much lower herd immunity threshold. It's that we're seeing the natural waxing and waning of transmission that happens as collective social behavior and the decisions that individuals make aggregate and force the dynamics of the transmission. In fact, right, and this is another paper that Marcel wrote back in 2008 before he was at Stanford. It turns out that the herd immunity threshold can actually be higher than in the well-mixed model. And bear in mind that, it's like 3/4 of the population in the well-mixed model. And guess when that happens? Well, it's when you have strong population clustering, as in the case of this homophily and outgroup aversion model. So rather than a threshold being around 20%, as with the heterogeneity model, it's possible it's more like 80 or 90%. This is not something that people throwing around the lowered herd immunity threshold talk about or maybe even know about. And so here is a figure from Marcel and Sebastian Bonhoeffer's paper in 2008 that they call it opinion clustering. I call it homophily, right? When you are surrounded by people who are like you and behave like you and have the same attitudes towards control that you do, you actually raise the likelihood of an outbreak in the case of a childhood illness such as measles, or you also raise the herd immunity threshold. So I actually suspect that it's higher rather than lower. All right, so those are my main results. Let me just conclude briefly with telling you what I've told you already. Okay, epidemic models need social behavior. Social behavior is built into the formalism of mathematical epidemiology through the mass action term and the SIR family of models. But there's a real dearth of contemporary work that takes social structure seriously. We need more collaborations between the fantastic mathematical epidemiologists and other professionals working on epidemiologists working on pandemic control. Most of these mathematical epidemiologists, by the way, are in biology or ecology, evolution, and behavior type departments, right? And we need more collaborations between them and the epidemiologists and quantitatively sophisticated social scientists. Yes, we exist. And I think they're important, interesting scientific and policy questions to address. We have a science for behavior change, right? So much of pandemic control and other problems, the dealing with other problems involves behavior and culture change. We have a science for that. It's called cultural evolution. It gives us insights like uncertainty leading to conformist bias or to error management, right? We need to do two things though. We need to get these very smart people involved in important applied work such as pandemic control. We also need to get more smart people studying this field. There's a lot of really interesting questions out there, and I see a very bright future for the field. So I hope we can get more people engaged in this. Control is going to fail if we don't account for heterogeneity. And the reality is we've known this since Annette Nold in 1980 made this observation that the likelihood of an outbreak was directly proportional to the variance in contact behavior in the population. This is a point that Roy Anderson and his colleagues elaborated on greatly in the context of the AIDS epidemic of the 1980s. This is something we've known in mathematical epidemiology for a long time, but it seems to be a hard lesson to learn. Why does that matter so much here? It matters because social scientists are engaged in measuring heterogeneity. That's really what social scientists do. And they can bring a lot to the table for thinking about how populations are structured and how behavior is mediated by social structures and how that's likely to affect epidemic outcomes. Control will fail if we don't account for social structure, right? Particularly when the structure is formed around identity groups who are at odds with each other and at odds with scientific and political consensus. This is another wide open area that I think there are a lot of really interesting empirical questions as well as more theoretical questions we can deal with. And then finally, heterogeneity and selection are not going to save us. We probably need to vaccinate more rather than fewer people based on the sort of well-mixed expectations. So I'm going to say we need to probably vaccinate a good 80, possibly 90% of the population because of the social structure and the homophily that we see particularly in the United States. So it actually raises the herd immunity threshold from that predicted by the well-mixed population. So that's what I've got to say. I thank you for bearing with my kind of long talk. And I figure, when in doubt, withhold tacos, right? That would change my behavior. That would absolutely change my behavior. If I wasn't wearing a mask and couldn't get tacos, I would go find myself a mask. Maybe we can find things like that to help with our behavior change in pandemic control. All right, thanks so much.